So let's grab a look at this question in full now. I'm projecting this now from the PowerPoint. You'll see as well that I've got a bunch of additional questions, and that's what I would actually do if I had a question like this on a test. I would actually throw in some more questions here. Let's grab a look at this. On the right, we have two boxes connected by an unstretchable steel rope. Now, unstretchable implies, guess what? You don't have to stress about Hooke's law. The rope is hanging on a frictionless pulley. That means you don't need to worry about the friction in the pulley, because sometimes you do. And it's on a frictionless ramp. So cool, we don't have to worry about friction. That's pretty nice. What is the component of force acting perpendicular to the slope? Well, perpendicular to the slope means at right angles to the slope. So what the first thing we should always do is we should always draw in the forces that are acting. Let's draw in, the first thing let's do is let's put in all of the forces acting on, as many of the forces as we can. The first couple of forces I want to put on is, we've got this force of gravity. Now there's no force of friction, so I don't need to worry about that. The only other force that's acting on this block is this force here, which is the tension force. Okay, the force of tension. Now that tension force is going to be essentially contributed by this force here. This block here is going to be pulled down by gravity, so we're going to call this one Fg. It's going to be different from this Fg, but it's the same. And of course, it's going to be pulled up by a tension force. And these forces, and of course, we can start to calculate what these forces are to figure out what the net force is, and so on and so forth. But these are just the forces acting. Now, once we've got this downwards force, the next step to do with any type of inclined plane is to draw in two additional forces to break this down into components. And those components, and this angle here is 35 degrees. Those components are the force of gravity parallel to the slope and the force of gravity perpendicular. Now that side, now it's getting a bit messy here, but we just need to survive a little bit longer. That slide is adjacent to the slope, and this slide is opposite to the slope. So if I want to calculate this adjacent side, let's do some maths up here. Pardon me. Let's do some maths up here. Let's go with the adjacent side. That's going to be cosine theta. Cosine theta equals adjacent over hypotenuse. In this case, our hypotenuse is Fg. So we've got, if we want to figure out the adjacent side, we've got h times cosine theta equals adjacent. Our adjacent side is Fg, because that's the force of gravity, times cosine, and this times theta of 35 degrees equals A. Which A in this case, by the way, is of course Fg, but we're going perpendicular to the slope. So Fg, that's going to be mass times gravity times cosine 35 equals Fg perpendicular. Mass times gravity is 10 times 9.8 times cosine 35 degrees equals Fg perpendicular. So what that's going to give you is 10 times 9.8 times cosine 35 gives you 80.3. So Fg perpendicular is 80.3 newtons, which is what I think a lot of people said. I actually think I saw a lot more 80.2s because I think they've got the rounding wrong. But yeah, so that means this force is 80.3. So what is the component of the force acting perpendicular to the slope? I really should have said what is the component of. So that's going to be 80.3 newtons towards, we'll go perpendicular to the slope. Now, realistically, I probably should have rephrased that question just to say the magnitude of the force, the size of the force, because, yeah, the direction that this is applied, obviously this is the force pushing into the slope. So guess what? The normal force the slope pushes out is going to be the same, because that's going to balance this out. So maybe I'll draw that in. So that's going to balance that out, and that's going to be the normal force. And I could have just said calculate the normal force. That probably would have been good too, but I thought, no, I'll probably say perpendicular to the slope, because one, you guys might not be familiar with that terminology, but yeah, some of you guys would. The next thing is to calculate the component force acting parallel to the slope. Now, this is the one that we actually really care about. This is because ultimately this perpendicular one, we can't really do much information with. What we sometimes see is sometimes people see, oh, the normal force equates to friction. The greater the normal force, the more the friction. And so therefore you can actually use that as a bit of a, as an extra sort of thing that you can use to calculate. I have seen that in questions, so do be aware of that. But yeah, what we're going to look now is at sine. We're going to look at this angle here. So we're going to look at sine theta, because it's now opposite and hypotenuse equals opposite of a hypotenuse. We've got hypotenuse times sine theta equals the opposite. What we've got is we've got FG times sine 35 equals FG parallel to the slope. So that's going to be this force downwards. And that's actually one of the forces that we really care about. So that's going to be, again, mg times sine 35 equals FG parallel. That's going to be 10 times 9.8 times cos times sine 35 equals F parallel. And I'm running out of room here, so I'm just going to write the answer up here. The FG parallel to the slope is equal to, and I'm using these symbols, by the way, for perpendicular and parallel, just because it's a shorthand for me. It makes it a little bit easier. The ultimate answer is going to be 9.10 kilograms times 9.8 times sine 35 is going to give us 56.2 newtons. Beautiful. So that's this force here. 56.2 newtons. Okay, so 56.2 newtons down the slope. Beautiful. Or you could just write parallel to the slope, whatever. So now we're actually, it might look like we're not really, we haven't really made much progress, but actually we've actually come pretty far through this question. The rest of this question, in my opinion, is going to be pretty easy. We're going to now calculate what is the net force acting on the block. Okay, so we've got 56.2 newtons downwards. Okay, obviously the normal force and the gravitational force, they're going to cancel. So I'm going to ignore that because it doesn't really matter. Okay, what we do care about is this force pulling downwards and this force pulling upwards, this red force, tension force. But that tension force is caused because of the pull downwards by this gravity. So what is this gravity? This is going to be F equals mg equals 6 times 9.8. 6 times 9.8 equals 58.8. 58.8. So that means this force upwards is going to be 58.8. And stop. I'm actually about to make a really big mistake with doing this question. One of the advantages of hindsight and recording these things is I can actually go back and fix up that mistake and show you where I went wrong. So let me just put up this slideshow and quickly show you guys where I made a mistake. And I completely forgot about the fact that these two objects are connected, and I'll show you how to do this properly. Okay, so future Greer here, it's showing you guys where I made a mistake. So what I just said was the force upwards was 58.8. And that makes sense because it's like, oh, well, it's the only thing pulling it down. Except for the fact that we've got a bit of a problem here.
that 58.8 that's pulling that object down has to also pull this mass here. So what we have is we have a bit of a problem. We have to stop now and look at the total system. So if we look at the net force on the total system, I'm going to do this up the top here, net force on the total system, we've got this force here, which is this 58.8 newtons pulling it downwards. And then we've got this 56.2, which is pulling it down the slope. So that's acting in the opposite direction. So I'm going to go minus 56.2. And that's going to give me the net force acting on the whole system is going to be 58.8 minus 56.2 equals 2.6 newtons. And you say, oh, but that's the same number I just put here. But, and this is the clear part where I made the mistake, this 2.6 newtons is the net force of the whole system. That means that I can't just write that 2.6 here, because that 2.6 is the net force of the whole system. So what I might do instead is find this. What is the, if I know the F net equals 2.6, then I know that that's going to equal the mass times acceleration. And I know the total mass of the system is equal to 10 plus 6. It's going to be 16 kilos times the acceleration. 2.6 divided by 16, 2.6 divided by 16 is going to give us 0.16. Let's go with that. The acceleration equals 0.16. And that means the acceleration of this one is 0.16 meters per second squared, and the acceleration of this one is 0.16 meters per second squared. Okay, now we know that F equals ma. We've got mass is 10 kilograms, our acceleration is 0.16. So our net force is 1.6 newtons. A little bit different from our 2.6 up here. So that means our net force is 1.6 newtons upwards. Still upwards because ultimately we're still accelerating this way, because this way is still going to go up, but it's just not the same force. 1.6 newtons. Now we can also see, by the way, is that we can see here for the next answer, what is the acceleration of the 6 kilogram box? Well, that's quite clearly 0.16 meters per second squared, because that's the acceleration of the whole system, now that I've got that correct. Now, the last question here that I did do correctly, if there was a net force, the answer is still no, because ultimately no, because it would exceed the net force, and so there would be no movement, therefore no movement. But I think as a bonus little extra thing, what I want to do, and this is bonus just because I didn't do this and it wasn't actually a question, but I think this is what drew my attention to the fact that there was something wrong, was I wanted to go, well, what, I thought to myself, this tension force here and this tension force should be the same. And when I was like playing around after the lesson, I got you guys to start working, I did these calculations and they were different. And that's what made me go, wait, what's going on here? I've made a mistake. And it took me a while to figure out what the mistake was. But this was the mistake here, that I was not looking at the whole system. I actually thought that that was just a problem with this question here, but it turns out it was a problem with this question too, because the net force is not 2.6, it's actually 1.6 on that box. So now let's look at this. Well, what is the tension force? Well, let's grab a look at this part down here. If I now know that if I've got a, and I'm going to do that, I'm going to probably do some working out down the bottom here because I'm running out of space here, ladies and gents. Normally, if I had a massive whiteboard, I would be fine. But if I've got 6 kilograms, if I've got 0.16 times, in this case 6, because F equals MA, means our net force is going to be times 6. It's going to be 0.975. That means the net force needs to be the net force, F net, is going to be our gravitational force downwards, which in this case is 58.8, minus our tension force upwards. If I've got 58.8 minus the force, and that's going to equal, that means that sorry, let me just rearrange that. If I take our net force and I subtract 58.8, that will give us the negative tension force, or the tension force, the other tension force. So if I do this really quickly, the net force, which was here 0.975, 0.975, sorry, I pretty much lost that 9 there, 0.975 minus 58.8 equals the tension force. The tension force comes out to be equal to, let me do this on my own calculator, minus 58.8. 58.8 is going to give you 50, the answer comes out to be 57, rounding it up about, so we'll go with 57.8. We'll go with 57.8. 57.8. Okay. Now, that's cool. That's the tension force. But let's compare it to this one. Well, let's just do a little bit of extra. A little bit of extra work's never really hurt anyone. Let's just find this one here. Now, we know the net force here is actually 1.6 newtons. And that 1.6 newtons is made up of this tension force, which is pulling it upwards, minus this 56.2, which is pulling it downwards. Now, if we then go, well, 1.6 equals the tension force minus 56.2, that means that 1.6 plus 56.2 equals our tension force. Our tension force comes out to be 1.6 plus 56.2 comes out to be 57.8. What do you know? It's the same answer. And that is the part. And once I got that, I was like, right, I got it. Because it makes sense that the tension force would be the same. Because ultimately, if the tension force was larger on one object than the other, then that would imply there was a net force acting on the wire, which would imply that the wire is actually being stretched. And we know that it's an unstretchable steel rope. So that's why I was like, there is something wrong here. Now, luckily, we don't need to worry too much about it, but we do need to worry about it here. Anyway, I'm sorry I made a bit of a mistake. Maybe this has helped you. Maybe this has just made you more confused. If it has, please let me know. I'm more than willing to go through my own thing with you guys later on, but hopefully that helped. I'll chat to you guys later. Good luck for the test. Bye.